the Big Bang was not the beginning. The Big Bang was followed from the remote future. And what happened before was this exponential expansion, because it's just like what we see now in our eon. This theory tells us that there is no beginning and no end, because Einstein originally put it in for two wrong reasons. And he told me, look, you're wrong. And I said, I'm wrong. We live in a galaxy. We are on a collision course with the Andromeda Galaxy. You can see it. The Andromeda Galaxy and us, we will collide. When we collide, these black holes will feel each other out. Basically, they will swallow us. That's the boring era. When you have the black hole sits around for about 10 to the 100 years.
And the first question is, what do you think, what came before the Big Bang?
Well, you see, I have this scheme, which actually originated in something like 2004. It's not new, but very few people take me seriously. The view has evolved. There are observational consequences of the view I have. The view is that the Big Bang was not the beginning. The Big Bang was followed from the remote future. It's a hard thing to get your mind around. This is why very few people take me seriously, because you see, it's telling that the very remote future, you see, in the current view of current cosmology, apart from inflation, which I don't want, inflation was introduced for some good reasons. I'm not saying it was for bad reasons. There are good reasons for introducing inflation. It's just that I have other reasons which supersede those reasons. And the argument is that in a certain sense, you see, the inflationary picture says right after the Big Bang, there was expansion, this enormous exponential expansion, which increased the size of the universe by a huge factor, but in a tiny fraction of a second. Now, what I'm saying is that that is a misleading picture, is that that did not happen. You have an exponential expansion, but you're looking through the Big Bang to what happened before. And what happened before was this exponential expansion, because it's just like what we see now in our eon. I use the word eon, A-E-O-N, to describe from a Big Bang to the remote future. So we had our Big Bang. It's what currently people think is the whole of cosmology. I say it's not the whole of cosmology, because the Big Bang to the remote future, we have this exponential expansion. We now observe the universe to be expanding in this exponential way. That is to say, the amount of expansion is the same. Well, the size, if I can explain what an exponential means, see, people tend to use exponential and say, oh, very, very big. It's not that. It tells you that it's self-similar in a certain way, that the expansion continues in a self-similar way. So that's what we seem to see. It is a consequence of Einstein's theory if you put the term in, which is called the cosmological constant, which has a very curious history, because Einstein originally put it in for two wrong reasons. He then tried to take it out again, because he regarded his greatest blunder. However, it turns out that his greatest blunder was actually true, that the cosmological constant is there, and you see this exponential expansion in the universe. People call it dark energy, which is a terrible word, because it's neither dark nor is it energy in any ordinary sense of the word. So it's not dark and it's not energy. It's not dark energy.
Have we ever known the nature of Big Bang? We have no lights from the time.
Oh, indirectly, sure. I think we know quite a lot about it. Not the inflation, because there's a lot going on after the inflationary phase if there wasn't inflation.
What's wrong with inflation theory?
What's wrong with it is that it wrecks my theory.
There's a first
You don't
point.
need it, you see. No, in the scheme I put forward, you don't need inflation. If you put it in as well, then it spoils the cosmology. So you don't need it, because there is already an exponential expansion. It's not after the Big Bang, it's before the Big Bang. So that these effects which look like inflation are not due to inflation, they're due to peering back through the Big Bang into an expansion which was an inflationary expansion. Because it was like what we see now. Our universe, our eon, let's put it like that, has a remote future which we are already seeing, this exponential expansion, self-similar expansion. And that picture is completely consistent with observations. I like to say I had a time when I didn't believe it, and I changed my mind. You see, I think it's a good thing to have changed your mind on certain things. So I had to change my mind on that one. I didn't think it was there originally for wrong reasons. I had a wrong reason for believing that the cosmological constant had to be zero. And then I remember being convinced by Jerry Oestreicher, who was a Princeton cosmologist at the time, and he told me, look, you're wrong. And I said, oh, I'm wrong. Wasn't quite like that, but yes, I believed him. I could see his arguments, and I had to go back and think through what I said, and I got my reasons are not good, and I changed my mind. So that was when I changed my mind to believe that there really was this cosmological constant, which is positive, which gives us exponential expansion. Then, ultimately, not immediately, but I guess it was in 2004 when I first gave a talk about this. Actually, I'm not quite sure when the first time it was public, because I gave a talk in a television interview, which is very curious.
That was beginning, but what will the end, the universe?
There's no end. It goes on, you see. No, the exponential expansion of our eon.
There is no end of universe?
Well, they might be wrong. I'm not saying this theory is the ultimate truth. This theory tells us that there is no beginning and no end.
So that's why you create a cycle universe concept or theory?
Well, you can call it cyclic, yes. It's cyclic. The word cyclic means it goes on and on and on and on, yes. We live in a galaxy. We are on a collision course with the Andromeda galaxy. We can see it. And I am told by astronomers that the Andromeda galaxy and us, we will collide. Okay.
But it will be maybe the end of our galaxies, but not the end of the universe.
No, not the end of our galaxy, no. They will probably go through each other and then come back and settle down and become a bigger galaxy. Andromeda is bigger than us, so mainly it will swallow us. We have a black hole in the center of our galaxy. Nice, impressive observations that my colleagues made. Picture comes from standard cosmology. Standard cosmology tells us in the center of our galaxy is a black hole. In the center of the Andromeda galaxy is a much larger black hole. When we collide, these black holes will feel each other out and swallow each other up. Basically, they will swallow us. That's to say, the Andromeda black hole is much bigger than our black hole. It will have us for dinner. Okay.
Do you remember the time that you invented the most important theory regarding to the black hole?
I don't know. You see, we can't make that prediction. It depends on too much detail. You see, you would have to know how much they miss by, what the dynamics will be, how long it will take for them to capture each other, when they will spiral into each other, and then there will be this explosion as they swallow our one up. That will be almost unpredictable, I would say. But it will be many, many millions, thousands of millions of years from now. A long time. Then it will start to gulp down the whole cluster. You see, there are about 4 or 5 galaxies in our cluster. It's a small one. Mm-hmm. There are bigger clusters which contain millions of galaxies. They will eventually get swallowed by a supermassive black hole. It starts to swallow the stars. Most of them will go into a supermassive black hole. That black hole will sit around. That's the boring era. When you have a black hole sits around for about 10 to the 100 years. Think about 1 followed by 100 zeros. That number of years, long time, will be the kind of length of time that it will take for the black holes to finally evaporate away by Hawking evaporation. Now here's where Hawking comes in. So the Hawking evaporation, yes, sure. But that's a long time. Then that energy comes through into the next eon and makes a spot in the sky that somebody in the next eon could see. Now, also, I would claim there is another eon which happened before us. It had black holes, galaxies, clusters of galaxies. They swallow each other, form supermassive black holes, swallow each other, swallow. 10 to the 100 years, they gradually disappear by Hawking evaporation. All this radiation takes the energy of that galactic cluster. It bursts through in one little point into our sky, cosmic microwave sky. You don't see anything because nothing gets through at that stage. Nothing gets through until what's called the last scattering surface. The last scattering surface, finally, it bursts through and you see a spot in the sky. We do see these spots in the sky. We see these spots in the sky. Here is where paper, Christoph Meissner, Paweł Nurowski,
the Polish scientists.
Two Poles.
Two Polish scientists.
Myself, English, and a Korean, South Korean, who now lives in the United States.
Could you explain to our viewers your theory that was awarded by the Nobel Committee in 2020?
Yes. Well, you see, that was not on this.
Mm-hmm.
I don't think not enough people believe in this scheme. That's not got a Nobel Prize.
In the public opinion, you are a black holes inventor.
It came from black holes. But I should be explicit about this. You see, I was not the first person to think about gravitational collapse. There was a paper written by Oppenheimer, famous John Robert Oppenheimer.
Yeah, from Los Alamos.
Yes, from the famous movie was made recently. But Robert Oppenheimer also wrote a paper on cosmology. It was about a collapsing dust cloud. And you imagine this cloud of dust would collapse to what we now call a black hole. So that picture was already there. I knew it. I had read the paper by Oppenheimer and Snyder. Snyder was a student of Oppenheimer's. Now, this paper was something that people did not believe very much for two reasons. One is the cloud of dust which collapsed has no pressure. So what does dust mean? Material with no pressure. So that means there's nothing to stop it. It just collapses. Worse than that, it's exactly spherically symmetrical, like a sphere. Exactly symmetrical. Everything falls in towards the center. So you follow the particles into the center, and there is nothing to stop them, no pressure, and they form what's called a singularity, an infinite density. And that was the Oppenheimer-Snyder picture of a collapse to a big, what you now call a black hole. They didn't call it a black hole, but that was a collapse to a black hole. But lots of people did not believe that paper. Why did they not believe it? Because it's unrealistic. Why is it unrealistic? First, because there is no pressure. Normal dust is not like that. You have little bits and they knock into each other, or they might have forces which push them away or what have you. More importantly, it's not spherically symmetrical. There will be irregularities. As the further they fall in, the more complicated they will get. The collapse will be very, very complicated, and they swish around in some very, very complicated way and maybe come swirling back out again. So I think that was the common view, that the Oppenheimer-Snyder picture is a very nice picture, but not realistic. You would not expect a dust cloud to be exactly spherically symmetrical. The smaller it gets, the smaller you need the irregularities to be to spoil the picture. So the Oppenheimer-Snyder picture is not realistic when you get down close to the dangerous place where it goes singular and the densities become infinite and you can't solve your equations. So what I did, though, was to say, okay, let's consider an irregular collapse. Okay, it's like the Oppenheimer-Snyder picture, but it's not spherically symmetrical. And I had to define what I mean by it being collapsed as it's gone too far. So I defined a notion of what I called a trapped surface. That when you have it falling inwards a bit, and it can be very irregular, but nevertheless, it has a certain criterion which you can see. Does that criterion satisfied? If it is, you're in trouble. Because you then show a bit of mathematics, which of a kind which was not normally used in this subject, that you can use this mathematics to show there is no way of avoiding getting a singularity. Not unless you change your physical, if you have negative energy or some other thing which is not really allowed.
Do you remember this moment in your mind that you got the information, yes, I'm right, his mistake?
It wasn't exactly like that, you see, because the general argument I had formulated in my mind before, but I couldn't see how to use it in this case. And the conversation I usually describe to people was there was this friend of mine called Ivor Robinson, and he was an Englishman who was working in Dallas, Texas at the time. But he was an Englishman. I knew him quite well. He was very good with words, a very wonderful speaker. He could speak in very poetic terms, and the Americans loved him because he would speak in this wonderful way. And he was talking to me in his normal way as we were walking along. I was going towards my office, which was in London. And he was talking to me in this way, and I was interested in what he was saying. Then we met this road, a little road, which was a side street. As we crossed the road, the conversation stopped. Then we got to the other side, and the conversation resumed. And then he went away, and I went to my office, and I thought, I have a funny feeling of elation. Why do I feel like this? I'm feeling happy about something. Why do I feel happy? So I go through what happened in walking through the woods before I catch my bus, taking the bus, no. Taking the tube train, no, I don't see why. What I had for lunch, breakfast, no. Then I thought, when we crossed the street, I had an idea. And I was able to resurrect the idea. And I went into my office, and using that idea and techniques which I had already worked out for other reasons, I could see you could get a theorem which showed that you could not avoid singularities in this situation.
Do you remember the Nobel call from Stockholm?
I didn't actually go because it was during the pandemic and I was nervous of these things. And my wife was nervous and we decided not to go. And also it was a little bit complicated because they didn't have it. You see, that year when I got the Nobel Prize, they didn't have the Stockholm event for COVID reasons.
Mm-hmm.
And then I think it was 2 years later.
But the call was before by your phone. Probably the committee should call to you directly, inform you that you are Nobel Prize winner.
Oh, yes. No, that was a telephone call.
And have you expected, to be honest?
No. There had some little bit of a rumors about it, but I won't go into that. I didn't expect it, no. But you see, I had my secretary, and she phoned me up. I think I had to get out of the shower to talk to on the phone. I said, well, look, I can't talk now. What is it about? And she said, I think it's something the Swedish Academy of Sciences want to talk. I said, well, look, I'm sure they'll call back. So I go back into So I went back, and I thought, I wonder what that was. And so then they did call back, and the man started to talk to me on the phone, the director of the Stockholm, and he was talking to me, and he didn't explain what it was just yet. He said, oh, wait a minute, I have to make another call. I'm sorry. Will you hold on for a minute? So I held on, and nothing happened. I said, oh, I'll hang up. He said, if it's interesting, they'll call me back. So this was about the Nobel Prize. He did call me back eventually.
Never?
No, he did.
Yes, the third time. And then you get the information that you are Nobel Prize winner.
Yes.
Is it true that you made a bet with Hawking on whether information could leave a black hole?
No, I never made these bets. These are other people. Stephen Hawking.
Thousands of people talk about it, that it's not true.
No, I never made any bet with Stephen Hawking. Lots of people did. No, Stephen Hawking was a big betting person. No, he liked to make bets. Yes, that's
regarding
true.
to the science or
yes.
all issues around?
I don't know. A lot of it was the science, yes.
I have a very, from my point of view, very important question regarding to the quantum physics. You absolutely smashed the string theories and 11 dimensions. That was during the 20 years the subjects of the work of Krzysztof Meissner, for example, from Poland. Finally, he also decided to leave the string theory.
I wouldn't say that I'd
But
smashed it.
what did this theory give us?
Well, I mean, I can give you a little bit of history. I mean, I was never a fan. No, that's not true. When I first heard about string theory, this was from Leonard Susskind, I liked the idea because the very early version of string theory was a beautiful idea. You see, the idea, let me try and explain it. You see, quantum field theory, which is a very important part of physics, you think about particle physics and CERN and the big accelerator and how much money goes into that and all that depends upon certain types of calculations. Now, these calculations are largely done in terms of what are called Feynman diagrams. Now, Richard Feynman was a very great scientist. I knew him quite well. I appreciated his work very much. But he introduced this way of calculating in quantum field theory, which is a very powerful way of doing it. However, it leads to certain problems, that you get answers which are infinite. And the trouble is, technically speaking, if you follow the rules of the Feynman diagrams, you will get infinity almost at once. Whenever you have a diagram which has a loop in it, I'd have to describe what it means by a loop, but these describe physical processes which sort of go around in a loop. And when you get one of these loops, which you have to have them in the theory, it's got to be all over the place, then you find that the answer to these Feynman diagrams is, strictly speaking, infinity. So it's useless. But then it's not really useless because there are all sorts of tricks, many of them introduced by Feynman himself, tricks that you play to get around these infinities. You do what's called renormalize and play all these tricks. And once you have the rules of the tricks, then you can get good answers. I never followed all of them because it seemed like too much trickery. And I like to see why their answers are excuse me, rather than using the tricks, which I don't quite believe, you see. So I always felt it uncomfortable. However, when I heard about string theory from Leonard Susskind, and he told me, you replace these lines in the Feynman diagram by little tubes. Mm-hmm. So instead of having a line, which the line represents the history of a particle, instead of a particle, it's a string. You see a little loop, and that loop gets a tube. And then the problem comes in the Feynman diagrams. You see, when you have these vertices, you have lines coming together, and then you join them up and make loops and things, and you get into trouble, which the answers become infinity. But if you don't do that, you have these little loops which join up and they make sort of plumbing systems, which are you're not got any corners or anything, and they're nice smooth things, and all your calculations are finite. So I thought, that's a very beautiful idea. So I thought, yeah, I like that idea. That was the original string theory idea.
Mathematical one.
Yes. However, when the mathematical physicists got to work on this theory, they came to the conclusion that it does not work unless space-time has 26 dimensions. 26, 1 time 25 space.
That was so-called first string revolution.
That was the first.
Second,
that was the
and
first
then
one.
The second one. That was the first one.
That was the first one. And I said, okay, that's the end. I don't believe it. They had certain arguments that the
And still you don't believe it.
Sorry?
And still you don't believe it.
I don't believe it. But you see, then they said, no, we can get a better one. You see, you don't have to be 26 dimensions. It can be only 10 dimensions.
Or 11.
Yes, well then it gets 10 and 11 and 10 and 11 and 26 at the same time, and you have a mess of a theory. It started with this very beautiful idea, which, okay, if that worked, I would take that very seriously.
Now we know that we have 4 dimensions.
The fourth dimension apart from time, you mean? No. Well, I mean, you don't know. You see, they try to make out these extra dimensions are little tiny little loops. They're little knots in space-time. And because they're so small that they don't activate, and so that it doesn't work. The idea simply does not work. But I gave lectures and lectures about this, saying this idea does not work. Does anybody pay any attention to me? Not that I know of. So then I ended up, and I wrote a book. I think it's the last actual book that I wrote, which is called Fashion, Faith, and Fantasy in the New Physics of the Universe. And the Princeton University Press, they initially, they suggested the book. They didn't suggest the title. I suggested the title, and I gave 3 lectures, one on fashion, one on faith, one on fantasy. 3 lectures, yes.
And string theory belonged to the fantasy.
Yes, that was the
fashion. Fashion was the fashion.
Definitely the fashion. Because it was just so many people were doing it, that's all. They liked the beauty of the theory. See, that's the danger. I think you asked me this question, is the physics beautiful or something? Sure, it seems to be. When you get the physics right, it seems that every time it has its own beauty. I don't know why, but it seems to. Doesn't work the other way around. Just because you have a theory which is, I think that's a very beautiful theory, doesn't mean it's physics. That's the wrong way around. So the argument with the string theorists was they say this theory is very beautiful mathematically. I'm not even quite sure about that because it's so top-heavy in many ways. And it's a mixture of dimensions. You see, you have this thing they call M theory, which is 11-dimensional. And I'd written this book, Fashion, Faith, and Fantasy, and I understood that Princeton University Press kept on trying to make me change the title. Make it so, no, modern physics. You see, no, I want Fashion, Faith, and Fantasy. Okay, they finally agreed. It came out.
And it was published.
It was published. And only recently, within the last year, I had a communication from the Princeton University Press to say they wanted to bring out a new paperback edition of this book.
With the same title.
With the same title. And I thought, they're taking my title seriously. And so I wrote a preface, a new preface.
Will we ever achieve the creation of the grand unification theory?
Well, maybe we will.
What are we missing today?
I don't think it's the string. The string theory route is dead, as far as I'm concerned.
No, it's the second question for me. Another question.
Oh yeah.
If we ever achieve, if we connect the classical world and the quantum world.
Well, you see, there's the different worlds. You see, now there's a new in this. I do put this in the new preface. You had to write a new preface for the book, and I have a new way of looking at. See, when you're asking about my 3 worlds and three realities or something, there is a new division which I have of realities, which I have given lectures about, and it does appear in an article of mine. So it is published. But the idea is you can talk about quantum reality and classical reality, and physicists didn't seem to distinguish very clearly about this. Einstein gave a very clear definition of what he meant by what's called an element of reality. Now, to me, this is what I'm calling an element of quantum reality. I can tell you the difference very clearly. What is classical reality? See, an object may have a certain reality. It may have a certain structure, like this cup. You see,
yeah, this cup, for example.
I can say, "Hello, cup. What is your shape?" And the cup says, well, I've got a round top, it's a bit like a circle. I'm pretty cylindrical. I have a flat bottom, which is a filled-in circle. And then I have a funny-shaped little thing on the end, which changes the topology of the thing. And say, okay, I've got a pretty good description of what that is. So classical reality can tell you. You could say, hello, state. What do you like? What's your
shape?
Geometry?
What's your form?
Sure. What color are you? All sorts of things. Quantum reality can't do that. I could say, hello, state. What's your state? It looks blankly back at me. I don't answer questions like that. What I can do is what Einstein's concept of an element of reality is. And I like to give the example of a spin. You see a spin particle like a proton A proton spins about an axis, but it's a quantum spin. It's a funny kind of spin. You can think of it as right-handed about a direction, and that direction can be any direction in space. So its spin state could be that, for example. Now I can say, hello, proton, which way are you spinning? And it won't answer that question. However, I say to that proton, I can say, look, do you happen to be spinning about that axis, right-handed about that axis? And then it can say, yes, you got me right. And then I say, okay, I tried again tomorrow. Are you spinning about that axis? Yep, still, same state. That's Einstein's definition of reality. Now that's quantum reality. You can confirm your question and your measurement does not disturb the system.
But what's the bridge between this quantum world, reality, and the classical one?
I can't say the following. Hello, state, which way are you spinning about? Are you spinning about that direction, that direction, that direction, or that direction? I won't say an answer. If you're spinning that direction, I can guess you're right and then ask, am I right? 100% certainty, without disturbing the system, it will say, yes, you're right. That gives it a quantum reality, but it doesn't give you a classical reality. Classical reality is something where I can ask the state, which way are you spinning? Not, are you spinning the way I think you're spinning? Can you confirm my guess or understanding that you're spinning that way? Yeah,
Okay,
I can confirm that.
It means that the bridge doesn't exist?
No, it exists, but it cannot be
But what is it?
ascertained. You see, it's the difference. You can confirm it, but you cannot ascertain it. See, I can't say, hello, spin, which way are you spinning? I can say it, but it doesn't answer me. I can say, are you spinning about that direction? Then it will say, okay, if I do that experiment 99 times or 100 times, then probably about 70 of them it will say yes, and about 30 of them it will say no. It's a probabilistic answer it gives me. It doesn't give me just yes or no. But that's the thing about spins. The spin is a definite state. It has a kind of reality, but it's not a classical reality. It's a quantum reality. So you have to make that distinction. And if you make that distinction, then you can much better understand the reality of quantum mechanics. And the quantum reality is not something which you can ascertain. You can't say, hello, state. I mean, you can say it, but it won't answer you. You can say, hello, state, what's your state? No, it doesn't answer. You can say, is your state this? I've worked it out that by now your state should be that. And then it can say, yes, you got it right.
When we are talking about this, everything looks very clear, but still the world of scientists looks the grand unification theory. So why we are so motivated to create a new theory after a theory of relativity?
You see, first of all, that this idea about reality is not a common view. It's something I introduced several years ago, but not many people have picked up on it. It's in the new preface to the, I think I must have put it in the preface. I meant to do that. But you see, there are various experiments. You see, the Nobel Prize, I think, 1 or 2 years after me, maybe 2 years, I can't remember, was given to several people about quantum entanglement. Quantum entanglement was where you make measurements over here, which seem to influence what's happened over here. This, again, is Einstein. Einstein, Podolsky, and Rosen introduced a concept.
1935.
Yes, I think that's about right, yes. Where you have entanglements. The state, you can think of it as spin states. That's a good example. The state may be, people like to talk about Alice and Bob. You see, Alice has a spin state, Bob has a spin state, A and B, you see. And so Alice makes a measurement, and she makes a measurement and finds the spin state is this way. That changes Bob's state automatically to be this way. Which faster than the speed of light? Seems to be. But Bob, it's quantum reality. See, if this was a signal, if it was classical reality, then Alice says, I've just measured it this way. Bob, your state is now the opposite of mine. And then he can then measure. He can say, hello, state, what is your state? And if it could say, yes, my state is this way, then that information could travel faster than light.
What we can expect from the next 100 years of physics? What do you think? Which grand theories?
Well, I have my own baby, you see. You see, if I talk about my own baby, this is, of course, a very biased view because it's a view that I put forward many years ago, quite a long time ago, actually. But only more recently has it evolved in a certain way. I would say the way it's evolved is about 2 years old. The theory is what's called twistor theory. I introduced these ideas the same year. It was the year when Kennedy was assassinated. I remember that because the idea came to me in the car. I was driven back from a holiday where we tried to recover from this tragedy. When was that? When was the Kennedy assassination? Do you remember? Anyway, this was in the... I keep forgetting the dates. 60s something. But anyway, that's when I first had this idea. I've been trying to play around with the idea. It's trying to bring relativity and quantum mechanics together, but in an unusual way. It's not going like string theory or changing the dimensions. No. No, you're sticking to the ones we see. 3 space, 1 time. Definitely 3 space, 1 time. Wouldn't work with a different number of dimensions. It's tied to that very number of dimensions. But it's based on spins, very much like that. It's based on how the idea of Ivor Robinson, other ideas of Ivor Robinson, bring him back again. He was an important influence. He and Engelbert Schucking. Engelbert Schucking was a German who had fled Germany before the war. And I learned a lot from him. He was a very, very influential person on me. Various ideas which I learned from him and Ivor Robinson. So those are 2 of the key people in developing the idea of twistor theory. So I had this idea of how you sort of extend the space-time, but you don't really. How would I put it? You extend the idea of a light ray. See, it's basically, you don't think of points as the basic things. You think of light rays as the basic things. And when they twist, they have a character which, how much they twist.
Do you think that it could be a revolution of the physics, twist theory?
I think I'd put some money on that, yeah. That you see, it's not finished. I used to have my class, when I was a professor here in Oxford, yeah, I had a group of people, a large proportion of them worked on twistor theory. There are many things you can prove in the theory. Lots of mathematical ideas. You can, beautiful integral formulae for things. You can write them down very neatly. And it's a nice way of talking about space-time physics. But not curved space-time physics. It's not really, it's special relativity. It's Minkowski-Einstein theory. It's not general relativity where your space-time is curved. Or is it? See, it's partly that. I mean, it has a very curious history because I combined it in one way, but this was very handed. It was only left-handed, and so you could only describe photons, which were in accordance with quantum mechanics and general relativity, gravitons. These were gravitons. So they could describe one gravitational entity, a graviton.
In your book, you just said that we need...
But I could only make it left-handed. You see, that was my problem.
Yeah.
And I had to make it right-handed, and that's what I call the googly problem, because that's a cricketing term. Can you bowl the ball so it spins right-handed when it looks as though it spins left-handed? I call that the googly problem. And then only eventually, I had an idea about 3 years ago, I guess, about to combine twistor theories with what's called split octonions. I won't go into what that means. There's a certain type of algebra, which I just thought it must be connected. And only because of the pandemic gave me time to think about it, I guess. But then there was a book which was going to be brought out by a Chinese person called Yang. There are 2 of them. One was called Yang and another one called something He or something. And this was about the 100th birthday of C.N. Yang. C.N. Yang was a well-known physicist who got a Nobel Prize were Yang and Li. They both got the Nobel Prize for discovering that a certain type of interaction in physics was handed. It was left-handed. It's the only thing we'd seen in physics which knew a difference between left-handed and right-handed. A remarkable discovery. And this was due to this man, C.N. Yang. Now, C.N. Yang, his birthday was coming up to become 100. And this other person, also called Yang, I mean, half the population of China is called Yang, so it's everybody almost. But anyway, this other chap, also called Yang, asked me if I would write an article in honor of C.N. Yang. So I said, yes, maybe I can write it on these bitwisters. So these are twisters together, the right and the left-handed ones together. So you bring them together into a new algebra, which gives you a new structure, and you can split the split octonion.